All right, so welcome back to System Software. Today we're going to be talking about building and a little on testing and debugging. So for homework last time, I hope everyone read the book, because it's a pretty lightweight read. Who read the book?
Yes, I did.
What'd you think? So what's some things you learned about C that you didn't know before? Yeah.
I didn't know debugging set breakpoints to pause and resume.
Yeah, I mean, GDB is one of the original or one of the earlier debugging tools, and if you ever use an IDE and it has integrated debugging for you, it's the same idea. Yeah.
I learned that the C language was 40 years old and did not require a corporation or foundation to spend money promoting on it. You also had a subsystem and several languages out there, and a bunch of important things that needed to run code.
Sure. Yeah. So stuff. It gives a history of C. And notice that the first several chapters of this book, even though it's a C programming book, there's no C involved. It's all about setting up your environment, doing building and testing. And so I hope you'll read at least the testing section so you can see some of the tools that are available for you to help you do testing, so you don't have to use kind of ad hoc, rewrite the same file, lose all your tests. There's some really simple things you can do to dramatically improve the ease of programming. And today we're going to go over makefiles especially, and a little bit on kind of debugging philosophy. But makefiles and build automation is something you're going to encounter quite a bit, I think, as a software engineer, as software becomes really large. Most people are doing maintenance on software. Most of the work of software is maintenance. And so you'll be working with a large project, most likely, and have to contend with the entire ecosystem around that code, which is itself substantial software products. Okay, and before I go on, so questions on the Hello World project so far? Yeah.
I tried to make it run and compile, but all this kind of I failed. That's not like I didn't fail, but I just don't know what else to do, because as of today, when I was replaying the script replay would replay.
It wouldn't replay.
Yeah. It would. I don't know. It wouldn't replay the recording. It did record, but I don't even know what happened now.
So yeah, we can look at that if you come to office hours or after class. We can check what's going on. But if you have a long delay, it may just if you took a long time to type when you started writing the script command, you have to wait that amount of time. So what you can try to do is put a larger number here in the replay, put like 10 or 20, and see if you just had a lot of time that went by. So this tool doesn't cut out time. There are other terminal recording tools that will detect pauses, but try this first. Yeah. Yeah. So next lecture is on version control, which we'll go over Git. So yeah, I wasn't expecting you to try to complete this project. These last lecture, this lecture, next lecture are really giving you the program environment tools to be able to submit this, what seems to be a very simple project, but as some of you probably realize, the tools around software, version control, build automation, are substantial. Yeah?
Does it matter if the first time I messed something up, so I went back and re-recorded it, so I didn't remake the files, I didn't use the original? Is that fine?
Well, you should record yourself typing the files.
Yeah, I went through and typed it and then...
Yeah, that's fine. Yeah. Did anyone? So I wasn't expecting anyone to do the Git yet, because we're going to cover that next time. But did anyone try to use Git to submit their project? Did anyone have issues with it? Yeah. What were your issues?
Mine said SMT reps match any, and then you failed to push some reps too, and then the big link that's on useless. So.
Yeah, mine said the host did not exist.
The host did not exist.
Yeah, I'm pretty sure I typed it correctly.
Okay. Maybe let's go over it on Thursday when we go over it. I'll show an example of doing it, and maybe we can catch something. I'd recommend cutting and pasting from here and not trying to type from. I mean, you can try to do that, but it's easy to make little typing mistakes. Maybe I made a mistake, or I think some people were saying that they couldn't connect to Eustace at all. So I don't know if Eustace was down, perhaps. But let's see if this server is. Oh, that's not good. Maybe it's only accessible on Eustace, or maybe I have the wrong name. Okay, so I can access it from Eustace. So make sure you do. Were you doing this from Eustace?
Yes.
Okay, so make sure. So this little ping command is kind of useful. It as long as the server is supporting ping, you can see if that machine exists. If it's like on, you give the domain name or an IP address. This is outside the scope of this class, but
We have to type in ping.
you just type ping space and then the domain name of the server or the IP address, and it'll just like come back. If it doesn't exist, so it'll say domain name not found. But if I give a IP address that probably doesn't have a machine, let's guess. So there's no machine at this address. It just won't. It'll say unreachable. So that'll give you a good it'll just give you a little sanity check about whether the machine is there, and then you can check the rest of the command. Make sure you're doing gitolite 3, so look at Brent. Brent put out an announcement. He made the mistake of saying you should change this username. So don't change this username. This is the username that you're going to actually access on the server. There's a Git server there. So make sure this you don't change. The only thing to change is the NID. Also, if you don't have any content in your like if you haven't added anything yet, then doing git push, nothing will be pushed. So
You can check that by doing git status, right?
yeah. So we'll go over this next. We'll go over this on Thursday. I think most people haven't even attempted this yet, but we'll go over Thursday in detail using version control and setting up the Git repository for the Hello World project. If you have specific issues, feel free to come to office hours. I'll have office hours today and tomorrow, and I can see if there are any specific issues. But it sounds like at least some people got Git submitted. So I don't know. I don't know what the issues are. Maybe your name is not added. Maybe they missed your NID, or maybe the server was down temporarily. I'm not sure. But we'll work it out. But you have plenty of time. You have plenty of time to do this. And if you've done all the rest of the project, you'll have another 5 days after that to get this done. All right, no problem. All right, other questions on the Hello World project. So I put a plan for this, which I only probably outlined briefly in the lecture, was last time going over the editor, and so there's 3 pieces here to this project. One is actually using an editor that maybe you've never used a command line editor before, but using the editor and recording yourself doing it. The make file corresponds to what we're going to go over today, so making build automation for your project, and then submitting your project via Git is what we're going to cover on Thursday. So the homework is really light; it's just reading, and the idea is that you'll work on this project incrementally. So each lecture, you'll learn the new step you need in order to complete this seemingly simple project, but learn the ecosystem around this project. Yeah.
Every time
Yeah.
I open up a file, it opens up a separate thing. That's what you dash and W to do it within a terminal. Is there a way to
And that's when you're logged into Eustace. So you may be connecting to. So I saw that comment on EdSTEM. So the reason for this may be that so this will happen on my machine where I get a window. So that shouldn't happen if you're logged into Eustace, but the reason I suspect it might if your terminal is getting into the weeds, but you can actually, it's like remote desktop. You can actually remotely use a windowing interface on Linux, and that your terminal may be setting a flag that forwards those, but it basically does that remote terminal session. Let's see if that's actually the case. So if I run Emacs here, am I going to get a separate window? I might. It looks like I am, actually. So I would just reconfigure your terminal to, it's -Y or -X is the flag for doing it. So if you find some setting in your terminal, or just use Emacs NW. And NW means no window. So it'll run so I think this is actually giving me it's very, very slow, but looks like it's doing the windowing interface. You can also check this environment variable. Remember we talked about environment variables? If you print this one, the money sign display. So it looks like, indeed, I've got a remote window session going on Eustace. I didn't know Eustace supported that. I don't know if they meant to support that, but yeah. So apparently you can open up windowing applications on Eustace and have them displayed on your machine, like remote. Yeah. So I think that's what's going on. So check for settings in your terminal. I think it was MobiTerm, right, or MobiTerm. Check for like a setting for forwarding X11 or remote desktop or something, but it's probably like forwarding X11 is the SSH, is I think of the name of the SSH command. X11 forwarding, yeah.
When, I know one of the requirements is to record yourself.
Yeah.
But if I'm working on it in different ways, how does that work?
Well, you only need to record yourself typing the Hello World program, not everything. So the instructions are just this part, only these 5 steps. So I'm assuming you can write a Hello World program, in one day. And so you can Google it. Hello World programs are they're not secret. So I expect that you'll be able to do this quickly, I think. But you don't have to record the whole project submission. Only the opening the editor and typing in the Hello World program. That's it. You don't have to record yourself compiling it or doing make files and all that. That might definitely be it'll definitely be multi-day. Does that answer your question?
But so if
Yeah.
I record myself writing a little note and all that, does that not come at the end? Like, is that first step of creating the file?
Yeah, I mean, well, at least the way I've laid it out is the first step is to just create the Hello World file, and that's it. So let me show this. Let me show this again. What this looks like. I think I've got a hello. So following the directions here, so it'd be make directory hello world, change directory hello, and then start recording. And so if you've at least done the tutorial of the editor, you should at least at a minimum be able to create a new file, open a new file, type it, and save and quit. So here's starting the script. And so the timing is recording now. So any long pauses you have here will be replayed back in real time unless you add a multiplier. And here I'm going to use Emacs because I'm an Emacs user. And then you just type in hello world. And feel free to look at, I'm giving you the hello world code. You can copy what I do for hello world. It's no secret. The point of this project is to learn the editor, make files, build automation, and version control. So the actual coding step, I tried to give something that is something, I think everyone has done. And so use the editor commands to save. So I did, Control X, Control X, Control S, Control X, Control C in Emacs, and that's it. And then exit will stop recording. And so that's all I'm expecting you to record. That's it, just what I showed there.
And where's the script uploaded?
Okay, so if you look here, the scripts actually get saved here, and you can play it back with this command, which I'll just copy. And see, there's my delay from the beginning. Although even though I'm on 2x time, so I'm not no hands here. It's happening automatically, and you can quit anytime with Control C. So later on, when we do version control, I'll have you submit those files as part of your submission, so we can check them. Is that good? Okay, let's go. The make file. We'll go over that today. We'll go over the make file, how to do make files today. So the good segue, unless there are other questions about this part of the Hello World project. All right, so let's do what I think is a very exciting part of software engineering, which is build automation. I actually do research on this. It's probably one of the more boring parts, actually, of software engineering, but in recent years, it's become a particularly sensitive part of the software ecosystem. Actually, I hadn't planned to do this, but there was actually a couple of very large, severe security vulnerabilities related to the build system. One was SolarWinds, I think. Who's heard of the SolarWinds attack? A couple of people. So this was a case. This was some, I don't remember what the software was. It was some security management software or something. So yeah, they do management. They do organizational management. Where's the attack? So the way attackers got in, so this software is, it's all certified and digitally signed, so that when you receive the software, you can be sure that who you thought made the software actually made it, because they have a private key that they use to sign the software, and that's very hard to break. So what the attackers did, instead of trying to put malware on some of their target machines or try to make a fake version of this software, they broke into SolarWinds digitally, they broke in remotely, and they modified the build system to insert malware into the software before it was digitally signed. And so this is something that's a little tricky to detect. Instead of inserting it in the code where some sharp programmer might notice, you insert it into the build automation, because the build automation can do whatever it wants to the source code during the build process. What was that?
Is that thing on
Yeah. So this is how a huge number of organizations were attacked. So another more recent example is the libxz attack. Who's heard of the libxz? Even fewer people. So this one was particularly nefarious. Let me see if I can get the details right. But basically what it did is it allowed, it put a backdoor in the SSH server of any machine that was infected. So this could be Eustace, this could be any server you run, would have a backdoor that I think allowed whoever created the software to access that server. But the subtle part here is that it wasn't a direct attack on the SSH software. It was a direct attack on this compression library called libxz. And that library actually is not linked to SSH. SSH does not use this library. Instead, it's used by, remember we talked about the init process the other day. Let's see if I can bring this up again. There's an init process. Well, actually, I can show the process here. So this init process on a lot of modern Linux distributions is actually a program called systemd, which basically manages all of your background processes, including SSH servers. So they're not going to let me. They do let me see this. Okay. SSH is one of the services that it runs, and apparently, from my understanding, which might be a little wrong in libxz, that systemd depended on this compression library, libxz. But it also is the process that's like running SSH. And so apparently, this person very cleverly got code into libxz that would modify systemd to put a backdoor in the SSH running process. So it's a complicated sequence of how the attack was. How it was discovered was very funny, because I think some Microsoft engineer noticed their SSH logins taking like a second longer. Which seems like, but it was like, 20 times longer or something. So a second seems like not a lot, but if it's 20, whatever it was, 10 or 20 times, it was slower. But the way this attack happened was not, so this maintainer, there's a couple things that were at play here. This libxz library, like a lot of open source libraries, was just maintained by volunteers and may not have a lot of activity. And so some user over some long period, this long con, got themselves effectively maintainer status on this project. They could do whatever they wanted to the source code. And they didn't insert a backdoor into the code. What they did is they made a test. So libxz has its own test being shipped with it, as I hope you read about in chapter 2. Has a suite of tests. And so they inserted the malicious code into one of those tests. The tests are compressed libraries, so they kind of look random. And so from what I understand, they put binary. Remember we talked about the name, what was that called? Masquerading names, the file system. You can name things whatever you want. So they named a test some compressed library, but it was actually some code, some binary code that would be used to modify systemd. And they shipped it as part of the build system, and it had some complicated build automation code that would not run the test, but would extract this binary code and insert it actually insert it into the libxz library, which would then infect systemd. So the process is very complicated. There's a really nice infographic. I can't remember where it is, but there's a really nice infographic on this that kind of explains the vulnerability. I don't like live searching, but there was a good infographic. Oh, yeah, this is it. So it's a complicated sequence of steps, but the main point here is that the malware was not just like written into the code. Instead, the maintainer decided to hide it in the build and test automation, basically the software ecosystem. And so while Makefile may be kind of boring and build automation is kind of this like hokey part of software engineering, because build automation is becoming so large. So for instance, the Linux kernel's 20 million lines of code. Its build and configuration system is like 200,000 lines of code. So who's written 200,000 lines of code here? I haven't, I don't think. Well, maybe collectively, but not in one program. That's a substantial piece of software in its own right. And so these are becoming targets, especially as software is becoming more memory safe or better vetted. The build automation software is kind of a Wild West. Doesn't have as much bug finding capability or safety as the main programming language. And so these kinds of attacks, you'd kind of expect would become more frequent. All right, so you interested in Makefiles now? Makefiles sound like fun. So I don't know if this actually used a Makefile, but it probably used some similar build system. I think it is a C program. All right, so with that impromptu prologue, let's get into build automation. So I kind of teased this already, but for you guys, for instance, when you built your Hello World program, what did you do to build your Hello World program? Yeah, you ran GCC, right? So you just ran GCC. That's how you build a program, right? Why do you need to do anything else? What if you have two C files that are part of the same program? You can write C code with separate source files, right? Has anyone written like separate source files for the same program? Okay, not bad. Okay, yeah. So in classroom projects, they're usually like 100 lines, 200 lines, not large, really no need. Why would you separate it into 10 different files? But for those of you who've done this, how do you compile a program that's composed of two source files? Yeah.
Basically, I would put the pipeline characters for both commands. I would just be, what I did was basically bash o main.c, and then I put the pipeline character. So that way you compile both. I think it's easier to I did two pipeline characters.
Did it look anything like this at all? Or no, use piping to actually cat them together? Is that what it's like? Oh, you compile them separately. I see. So you can do this with one line. If your program is divided into two source files, it's almost as if those two source files are in the same file, almost, kind of conceptually. What's that?
That's not the way you wanted me to say.
Oh no. Actually, what you're saying is you compile them separately is kind of what I would say the right way. You compile them separately and then you link them. So I think that's the right way. I was hoping for the easier way, the easier way to do it. But you're actually right. That is the right way to do it, which is do separate compilation, which I'll show. Yeah.
Does the order matter for when you compile it?
It may matter for error messages, like if you have the same function defined multiple places, the first one will be taken. I can't remember if order. I can't remember if order matters. I'm hesitant to say no, it doesn't. It shouldn't matter. It shouldn't matter because all the function names need to be unique. So it shouldn't, but I feel like I'm missing something. But this is like the kind of naive way to compile a program that has multiple source files. But what if I have like 30,000 source files? You have a question? Oh, okay. What if I have like 30,000 source files? Then what your colleague said, compiling them separately might be a better idea. Otherwise, you've got like this 30,000 file long GCC string. And so I wanted to actually show. So taking the Linux kernel as an example, here's a little find command. If you remember, I showed find a couple lectures ago. This will list out all of the C files that are in the Linux source code. And there's a lot. I can count them with WC. There's over 30,000 source files. So if you're building the Linux kernel, you probably don't want to have to build 30,000 files every time you're doing development, right? So yeah, so I'm kind of answering the question already, but why not build everything? Why not build 30,000 all at the same time? Why not do this? Yeah. It takes forever. So at some point you're going to have to do it. But one of the more important reasons is that if you make a change to one file, you're now going to have to rebuild 30,000 files, which is going to be really annoying if you're going to have to wait like an hour to rebuild because you changed one line of code. So the solution to this, as one of your fellow students pointed out ahead of time, is separate compilation. Divide your program into separate source files, which the C toolchain supports, and compile them individually, and then link these compiled files together. So I will, when we go into the compiler, I'll actually go into detail about all the steps that go into turning your source code into binary and a running process. But today I'll just show you kind of conceptually how you use separate compilation. So let me get, where is it? There it is. Okay, so the way this works is, this is not writing. Okay, there we go. Okay, that's weird. It won't write when I'm in full screen mode. All right, so the idea here is if we've got 3 C files that our program is broken down into, so let's make up a program here. Let's say it's content of the program doesn't really matter. Got 3 C files. So instead of running GCC once to compile all of them, we run GCC 3 times, once for each file. And these will produce what are called object files, which are the compiled versions of the C code. So we can compile each of them separately and use a tool called the linker. Who's heard of the linker? Did they talk to you about linking? A little bit, not much. So a linker will take binary compiled machine code and will turn it into a single program effectively for you. So now we've got our main .exe or main program here. So this is what separate compilation does for you. Seems pretty straightforward, right? You just compile each source file separately. Now you don't have to rebuild the whole program when you're doing development. You can just build one of the files at a time. Yeah?
So how does compiling these C files make it faster?
So it doesn't make, if you're just building once, it's the same amount of time, effectively. But if you're doing development and you're modifying parts of the code, then you only need to rebuild the parts of the code that you've modified. So this is useful for software development, not necessarily software users. So software users, you don't even need the source code. You can just take the binary if you want, if you don't want to build from scratch. But for a developer, if you're working on a large piece of software, which if you're going into software development, many of you will, you'll be contending with build automation and benefiting from it because it will allow you to rebuild more quickly. Yeah?
We use the same commands to execute the last one.
This one, the LD command?
No, the
Main, the main function?
Execute it the same way that we do here.
You mean executing main, like /main? Yeah.
It works the same.
Yeah. So it'll produce the same program binary. And actually running this... Oops. Running this version will actually do the exact same steps as running this version. The same steps. GCC will just do those steps for you automatically. It will do separate compilation and link them for you, but you just don't have those intermediate files saved. Yeah. So LD is a misnomer for the linker. LD stands for loader. I think it's a misnomer. So the loader is the part of the operating system that starts running the program. I think this was a mistake in the naming of it. I'm not sure, but it's the linker. This is the tool that will take binary files and glue them together into a single binary file. We'll talk more of that in detail when we get to compilers, how that works. Yeah.
What is the system, like if you have like 7,000 C files,
We are. So we're still GCCing each one of them. The difference is the real difference is whether we save these intermediate files or whether we save the individually compiled source files or not. So yeah, GCC will do the same thing if you pass in all the C files, but it'll throw away all of these intermediate .o files. And so you have to start from scratch with all the source files if you do it that way. Is that okay? Yeah.
And with this, for the linker, for LP, does that work for any coding language you're working with, or programming you're working with?
So that's actually a good point. So the compiler, and we didn't talk about compilers yet, but what the compiler is it's a translator from source code to machine code. So these are two different languages, actually. So this isn't a linker for C. This is actually a linker for assembly. Well, machine code in a particular binary file format. But you can think of this as a linker for machine code. So any language that translates into machine code, you can use the linker for.
And then the Java equals to that?
Java?
Yeah.
So Java does not, the normal Java does not compile into machine code. It compiles into Java bytecode for its virtual machine. The same linker won't work, but it does have a linker that will glue together multiple effectively. It will package them into one binary. What's that?
Is that like a jar file?
Jar file. Yeah, exactly. It'll compress them into one. Yeah. Yeah, good question. But yeah, so anything that is like compiling to machine code, like Rust or Go, Ada, will end up using the same linker or a similar linking process. So good question. Other questions on separate compilation? Any questions on why we do separate compilation or why people use this technique? Yeah.
I mean, is it what you said earlier about not needing those intermediate files or not just wanting to fetch them again?
Yeah, exactly right. Yeah, you just save. You save the intermediate compiled code. So if you think so this is more for like software engineering design. When you have a large program, you want to kind of chunk it up into logical pieces, and you can compile those separately. And the benefit of that is, you don't have to recompile the whole program. All right. So that's separate compilation. We looked at separate compilation. All right, so let's look at an actual example program. I've got this set up already here. So this program, I tried to make it as simple as I could. So it's a program broken up into three different C files. So there's one program, or there's one function here defined in exponent.c. This is supposed to compute the exponent of a positive exponent of a number. So don't worry too much about the code, but it's just computing the exponent x to the y. Square is a function that uses exponent to compute the square for some reason, but just an example to show you 3 different programs. And main calls square. Yeah, what's that?
The function has to be initialized in each of them.
Yeah, so that's why I have this. You couldn't use header files to do this, but I didn't want to overcomplicate the example. But yeah, square needs to be defined. I mean, it'll still compile without it, but you'll get some warnings. So yeah, that's why the function prototype here is declared.
But you don't have to declare exponent in the main.
No, because it's not called in main.
Oh, it's okay.
So only square is called. Yeah, and we'll go into compilation. Yeah.
Understand correctly, this is essentially what header files do in general.
Exactly. Yeah. So header files, they're meant to hold these declarations of the functions. I just wanted to keep this example simple, but yes, exactly. That's right. That's what header files do. Yeah.
Another thing about header files, I was just going to ask if there's any performance benefit to having a separate header file instead, rather than just putting all of the function declarations like at the top of the
Yeah, performance. So compiler performance. I mean, we're getting into these are pretty small numbers already. If you have a very large program, one benefit to having a header file is that GCC has an optimization called precompiled header files. So if they're included in multiple programs or multiple times, often headers get included multiple times, just because of the way the architecture of the different libraries or different components will depend on the same code, and so the same header files will be included multiple times, and so GCC will actually compile it once and then save the compiled version of that header file to improve performance. On the other hand, the header files may include lots and lots of declarations that you don't need, and so you could kind of optimize a little bit by doing what I did here and not using header file. Slight optimization. You have to open the file. You don't have to have all the declarations being parsed. Yeah.
It's like a basic example program, but in theory, if you were to actually make a program this simple, you probably would need separate compilation design.
Yeah, I mean this is like a design choice. The hard part here pedagogically is if I give an example where you really want to divide things up, I have to go through explaining the whole thing. But if I make it too simple, then you probably don't need to do that. Now, one reason you may want to do this is if, say, exponent.c is used in lots of parts of your code, you may want to put it somewhere separate. So if you modify that, you don't have to rebuild all the rest of your code. Maybe. But yeah, this is a totally contrived example where you don't have to break it up. Yeah.
Do header files have function definitions in them?
They can. So header files literally just cut and paste the code in, think of it as cutting and pasting the code. I mean, it actually does cut and paste the code. So you can. It's just totally a convention. So C imposes very, very little convention on you. But the way they're used, it doesn't enforce conventions, but the conventions that have grown up out of the C environment are that header files are defining library or declaring library functions, stuff that's in a different compilation unit. Or even in a different library. Once you get into processes and senior design, there's a software engineering course here actually that has been restarted by a great new faculty member. So I recommend taking those classes, and you'll see the larger software design and how you can use modules to break up your program. But you can even do it for in this class you could at least break things up into functions. You can decide whether you want to. The programs we're going to have are pretty small in this class, so you may not need to use this. But yeah. Other questions on this? All right, so there's our example program. Let's see how we separately compile it. So there's a flag in GCC called -c. And what it does is it does this step here. So running GCC-C will do just compiling for you. And in fact, -c is what compiling is. When you run GCC without -c, like in this previous example, GCC is actually doing much more than compiling. It's also calling the linker. and doing some other stuff for you. It's linking with standard libraries and the C runtime. So if you've ever run GCC and you didn't have a main method and it said, hey, you don't have a main method, that has little to do with compilation. That's actually a linker error. And we'll show more of that detail once we get to compilers. Has anyone ever seen that error? No main method? No? Okay. Okay, so here's how we can do separate compilation. So if we sort of agree that separate compilation seems to have some value, then why not actually do separate compilation? The problem is we have to like type this 3 times. We have to type have to individually compile each one of these C files. So let me actually go through the trouble of doing this. And now I've got my .o files. And once I got them all compiled, I have to run yet another command to link them. And so this looks very much like compiling them all together, but here I'm passing in the .o files, not the C files. So that process is going to be much faster. I think if you probably instrumented this, you would see that it's probably faster. Well, yeah, we can actually see that it's faster. So not much for this small program, but you can see that actually compiling took 4 times longer than just linking. So that's what we'd have to do if we want to take advantage of separate compilation. And that's kind of annoying, right? So if we modify main, then we're going to have to remember, all right, well, let me modify main here. And now I got to remember which file I modified, recompile it with GCC, and then relink it again. So kind of annoying, right? Little bit of memory stuff I have to do. So this is where build automation comes in. So sure, for 3 source files, not that big a deal. But when you've got like 30,000 and you want to have to manage this, we're computer scientists, so why not automate this for us? Why bother doing this by hand? Let's use automation. And this is where make files come in. Make files are designed to do build automation. They could be used for lots of other things, but they're designed around build automation. Okay, so this is called a recipe or a rule in make files. They have this very specific syntax. You put the file that you want to generate here, that's called the target. You put really just bash commands or a list of commands just like in bash. You put a little script here to tell you how to build the target file. And then prerequisites set up dependencies. And we'll look at how those dependencies work. But the main point here is we can declare, hey, I'm generating this file here, and here's the code to generate it. So very, very much like a bash script. And the simplest example of this is I want to generate the main program, and here's my command to do that. Here's how I generate the main program. This is my non-separate compilation version. I can just say, all right, GCC-O, and then all of the 3 C programs. With me so far? Questions so far on this? So this is the syntax of make. One little wrinkle is that this space here needs to be a tab character. It cannot be spaces unless you change the behavior of make. If you use a great editor like Emacs, that will like do that for you. This is the final version, but Emacs will basically do that for you. So, all right, so you can see here it'll actually show you, it'll highlight for you that you've got space here, and if you try to save, I think it'll warn you. Oh no, it doesn't warn me. Well, it'll show you the space at least. All right, so here's oops. So I don't have to type it. All right, here's my very first make file. So here's my make file here. And if you name the make file one of a couple of names, if you name it capital make file, I think there's a couple of other names, all you have to do is type make, and it will Let me get rid of so it's already built, so it won't build it again. So I just got rid of the file that was built. So when I run make by default looks for a file named makefile. This is the contents of my makefile. And what it does is it says, all right, you asked me to build, by default it'll build the first file in make. You could say make main. You could say please build main for me. And it will run this command. But make is a little smarter than that. It will, because this is the name of a file that you need to generate, it will not regenerate the file if it already exists. So because main exists here already, main will help avoid wasting time by just not rebuilding the file. You can force it, but I'll show you a more clever way to make it rebuild. But questions on this so far? Questions on the basics of a makefile? Yeah.
So if you were to have more, not just main, if you
Yeah.
have to make or run all of them,
It will only run the first one. So I could have a clean script here, which removes main, and make will only try to build main. So if I run make clean, it will run clean. So you can tell it which one you want. And we'll see that actually all you need is to, if you want to build a project, is to run the first one. And let's see how that works. But questions on just this, the basics of make files? Yeah.
Can you make a certain target applies to multiple files or like?
Aha, yes, absolutely. Okay, you're very good at segueing for you. But absolutely, yes, you can. You can. And we'll see that. Yeah.
They use it only with tabs.
Only with tab. You can configure it differently if you want, I think. But this is one of the annoying parts of Makefile, that tab is like part of the syntax. Yeah.
How do you do, like, you run that line and
I run make.
like you did the main tab still that, and then you said that it makes a make file?
Oh, so this is the make file. So if you look at my files here, I've got a file called makefile. If I use cat to print it out, this is the contents of the make file. Think of it as a program, and the make command runs that program. So by default, it will look for a file called makefile, but you can tell it which file to run. So think of it like a Python script or a Bash script, where make files are run by the interpreter make, just like with Python.
After you created it, it's called make file.
Well, you save it as a makefile. Like what we showed in file management or in editing, you save the file under a certain name. So you give it the name makefile, or you can give it any name you want, and then you run the makefile using the make command. Does that make sense? Yeah? Yeah.
so clean basically like it removes the output. Is that correct?
Well, this is what so it'll just run this command. And so that command,
Does it run it every time?
no, only the first, so make will run whichever target you ask it to. So it'll only run one recipe per execution of make. I mean, you can provide multiple targets at the same time, but this is getting into the weeds. But basically, you give it a target to run. So this is the name of the fake file I want to run, and here's the target I want to build. So name of the make command, file that holds the make script, and then the name of the target I want to run. And it will just execute the code here.
But then you can also just run make.
So make has defaults. So running make by itself will look for a file called makefile, and it will run the first target in your script.
Okay.
Yeah, so it's just defaults.
So then to run clean, we would just do the same thing we did before, but instead of main, clean.
Exactly. So we run make clean. We say the name of the target we want to
And then it'll
build.
erase out the
Because it'll run this command, which will end up it'll erase the output. Yeah.
So when we've called makefile and it contains main and GCC, correct? And then if you were to create another makefile, does that overwrite what the makefile contains?
Well, just like in any file system, if you overwrite a file, it'll be gone. You could make multiple make files. Yeah.
Just say if you did use call makefile multiple times, like in every iteration, like of the new one that you make, you have to include a command that removes the previous ones?
Well, the makefile, you don't remove the makefile. The makefile is like a program. It's like a script that you leave there. So when I run make clean, it's executing this command, remove main. So it's removing main. It's not removing the makefile. Does that answer?
I guess, okay, so if you run makefile, does it do both of them? Like, say clean had any other command, like not removing main, does it do clean and then retain main?
No, it only does the first. If you don't tell it any targets to run, it'll only do the first one. It'll do the first. So these are just defaults. These are just like convenient defaults. The kind of ideal is that you just download source code and you run make, and voila, everything's done for you. But that's helped by some defaults. So makefile is the default name, and then whatever the first target is the default name. So by convention, people use all as the first target, which I'll show you. But yeah, so there's just some sort of defaults here and conventions. All right, so that's writing a makefile. So why not? Why even bother to do this? It's the same as it was before. But we can add dependencies here. So what these prerequisites do is make will look at the timestamps of these files and say, have these changed since I built main? And so right now, if I try to rebuild main here, it'll tell me it's up to date, even if I go in and I say, well, I'll use the touch command to edit this. If I update main, it's still not going to rebuild it for me because it's already built. So the makefile system will say, all right, you've already built this, so I'm not going to build it for you again. But if I say, these are my prerequisites for building main, the makefile system will look and see if those files have changed. And if they've changed, it will rebuild this file for you. Make sense? Questions on that? So we can see that in operation here. So now if I rerun main, it will rebuild for me. And it won't rebuild main until I've edited one of the files. So if I edit square, and it actually just looks at the timestamp. So here I just did some minor edit, and it'll rebuild. Yeah?
So then the next step to this would be like you make all the compilations separately?
Exactly. So the idea here is you make, so instead of building the C files, we change this, we want to build the .o files, we want to just link the .o files, but we need to tell make how to build those .o files. So I want to build main.o whenever main.c changes, I want to build it. This is how I rebuild main.c. And then do this for all of my files. All right, so let me clean out all of the stuff I built. Oh, there are none. Okay, so now when I run make, the way this works is make will look at your prerequisites and say, has this been built yet? If it hasn't, it will go look for a target. Let me diagram this very quickly. So it'll take the first target we want, which is main, and it'll look at all of its prerequisites. So we've got main.o, square.o, and exponent.o. And it'll say, all right, I need to go build these if they don't exist already. So let me go look in my set of rules and say, do I have a rule to build main.o? Ah, yes, I do. So in order to build main.o, I need main.c to exist. I wrote that as a developer, so I don't need a target for it. It already exists. And it'll look and say, all right, has main.c been modified since I built main.o, or is main.o missing? If so, it'll run this recipe, this recipe, which, as long as you've written it correctly, it will build it for you. So the makefile is not going to ensure that you've written a correct build process. But as long as you have code here that will generate main.o, then make will run GCC for you. And it'll do this for every prerequisite. So it'll do this for square, it'll look for a target here, it'll do this for exponent. If there is no target available, make will give you an error. It'll say, hey, I don't know how to build this file. But if you've written this all correctly, then it will build all the prerequisites for you. Yeah.
So make file is looking for all those files within the same like parent directory?
Yeah, so these are relative paths right now. So you can use your knowledge about paths. There are lots of designs for make files. The Linux kernel has lots and lots of make files that are included inside of each other. But yeah, it'll just look in whatever your relative path is. All right, so what do you think will get run when I run make now? Or I run make main, which is what's going to be run by default. What commands are going to be executed? Yeah. What's that? So what's going to run first? Yeah, all the GCC commands we run, and then the linking run. So exactly what you guys predicted. And that's because it's actually building a tree of these dependencies and targets, and it's just going over the tree. It's using a tree traversal algorithm. It's saying, is this dependency old? Are its prerequisites newer than the target? And if it is, it reruns the recipe. If not, it moves on to the next tree. So just a basic tree traversal algorithm here. And the key trick here is if I now modify one of my programs or one of my source files. So here I add a comment. So I've now modified exponent.c. So you can see here exponent.c. Well, I modified it within. You can't even. The timestamp is more fine-grained than. Let me touch it again so you can actually see a change. So you can see this was modified at 114, whereas the .o file was built at 113. So when I run make again, what do you think is going to get run? Yeah. So it'll run GCC exponent.c. Anything else? It'll run main again, exactly right. So if I ask it to run main, it'll look through this tree, it'll look for the dependencies and say, all right, exponent has been modified. And it'll rebuild it, but because main depends on exponent.o, it'll say, oh, your prerequisites are newer than main. So because your prerequisites are newer than main, I should rebuild main. And that's exactly what we get. We get exponent being rebuilt and main being rebuilt, but nothing else, because everything else is already up to date. Questions on this? Is that cool? Is that useful? Okay, maybe not so cool, but it is really useful when you're doing large programs. You can declaratively say what parts of your program to build. Now, one of your fellow classmates asked, do you have to type all this out? Can you specify multiple targets? And absolutely you can. So you can do wildcard patterns. So we don't have to say each single C file. We can use this wildcard pattern to say any .o file with the same prefix .c file, run this. And there are all these esoteric built-in variables for saying, which part of the wildcard you want to use. So, you don't know the name of it because it's a wildcard pattern. This says the first, this basically says the prerequisites for this. So let me show you the sort of complete version of this. You can also make variables. These look super esoteric. This is the target name. This is the prerequisite name, the first prerequisite name. This is all the prerequisites. So I'll let you look at this on your own, but this is equivalent to this linker here, and this is equivalent to writing each C file at one time. And there's all sorts of other tricks like using variables and things like this in make. Questions on this? You can use wildcards. So last thing, if you want to have, so by convention, the first one's called all, the first target's called all. There's also usually a clean target. Now these don't correspond to any files. So if you want make to not check for a file and just always run it when you ask for it, they're called phony targets. You put this little thing here. So this is the complete make file for our program, and you can use this as a template for your much simpler program, which only has one compilation unit. So when you write your make files, you can use these notes as an example for your Hello World program. All right, so homework tonight is just reading chapter 3 and 4 of the book. All of office hours now. So, if anyone has questions, have a good one.